Hi, my name is Georgi Raduov. An operational oscillator circuit with diode-based limiter is given. The values of the components are given, and we are asked to derive the setting of the potentiometer P, so this one, at which oscillation will just start and slowly grow until the diodes D1 and D2, these diodes, stabilize the amplitude via soft clipping. In other words, what is the setting of the potentiometer P at which the Barkhausen criteria will be just satisfied? As an answer, please choose the most appropriate resistance between point P and the ground node of R1. So this is the ground node of R1. So this resistance, this portion of R1 should be given. Since R1 is given to be 60K, I can write that the other portion is simply 60K minus X. All right, here are the answers, and yeah, we have to select the correct one. Now we recognize that this is Wien bridge, and if you ignore the diodes, which turn on only when the amplitude is too high, what you have is a forward gain, which is non-inverting amplifier configuration. So these are the resistors, like this. And here, for the input, we take the input from the output through a bandpass filter. So this is our frequency selective network, which is like a bandpass filter. So this is VA, and we take the output here and we feed it to the input. This bandpass filter, of course, is composed by this part, where we have the high pass part and the low pass part. Okay, so let's recap quickly the theory of Wien bridge. Here we have RS and CS, just as one common impedance output, like ZS. We have here, say, node VC, and on the other side is the node VA, so this node, and here is ZP. Yeah, so this will be ZP and this will be ZS. We can now write quickly the transfer characteristic from VA to VC, so from this node to this node. We can write simply that VA divided by ZS plus ZP, and this is the current, is simply equal to this current, which is VC divided by ZP. All right, and now we are interested in the transfer of the bandpass filter, VC divided by VA, which is ZP divided by ZS plus ZP, or 1 divided by ZS divided by ZP plus 1. And we know that we can just represent ZP with it 1 over YP, the conductance, and then this will be 1 divided by ZS YP plus 1. Now we can expand. Here we have that ZS is simply 1 over SC plus RS, while YP, I'll just write it here, is the conductance 1 over RP plus SC. where we say that Cp equal to Cs equal to simply C and Rp equal to Rs equals to R. All right, now expanding here, what we get is that Vc divided by Va is 1 divided by Zc1 over Sc plus Rs times Yp 1 Rp plus Sc plus 1, and this is equal to let's expand 1 plus Src plus 1 divided by Src plus 1 plus 1. Yes. And we know that for sine wave signals S is j omega, and to have an oscillator we need that the phase from here to here is 0 or integer of 360, or in other words that the transfer is real. If it is not real, this means that the input output will come in different phases and there will be no stable oscillation. For this expression to be real, we require that this part, or the imaginary part, is 0, which gives us that the transfer at the frequency of oscillation is 1/3. From this point to this point, we lose 1/3 of the amplitude, which means that the forward gain here, this part, must provide a gain of 3 or a little bit more of 3 in order to have stable oscillations, in order to compensate for the loss of the frequency rotation network. Okay, so we require that this gain here, which is say I can name this RF and R ground, that this gain, which is say A1, is 1 plus RF divided by RG, and this is bigger than 3. Okay, so RF is R2 plus 60k minus X, while RG, the R2 ground, what we want is simply X. So now I can write here, from here, that I want 1 plus RF, which is R2 plus this portion. R2 is 15.1, 15.1k plus this portion, which is 60k minus X, and this divided by Rg, which is X, the R2 ground. So I want this to be bigger than 3. Then what I have is 1 plus 75.1k divided by X, and then I have minus 1. So this X divided by this X should be bigger than 3. This cancels out, this cancels out. So now I have X should be smaller, then I'll split this, 75 divided by 3, and plus 0.1 divided by 3. Or in other words, X should be smaller than 25 plus 0.1 divided by 3. So this is K, of course, K, K. Or X, the answer is that X is smaller than 25, it should be 25k here, this answer. All right, so this is the correct answer. Now you can see that we got, it should be here, this term, and this is that the answer we give should be in such a way that the forward gate exceeds just a little bit the Barkhausen criteria for oscillation, so provides a little bit more gain than the damping. So this is this portion, so that the oscillation start exponentially growing. And when the oscillation amplitude becomes too big, these diodes will turn on, will short a portion of the RF resistor, so this portion will be shorted, so only this will remain. The gain will drop, and this is how the diodes will stabilize the amplitude of oscillation. So for here, for the answers, if we choose too small a resistor, then the clipping will be much harder, because the forward gain when the diodes are turned off will be much bigger than the Barkhausen criteria. So this will lead to harmonic distortion. If we choose some of these answers, bigger resistor, then the Barkhausen criteria of oscillations will not be satisfied. So this is the solution. Thank you very much for your attention.